We are a team from NIT Surathkal and our project is called the low cost Dynamometer. What our project aims to do is to be able to measure the grip strength of a person and the strength the person and the force the person can exert between each one of his or her fingers. This project was basically developed for the Wenlock Hospital and KMC College's orthopedic departments, because doctors today do not have a method to gauge their patient's recovery when the patient is recovering from a surgery in their hands. The best way to gauge this is to be able to quantify the force that the fingers can exert on each other, as well as the gripping force. The present methods are very primitive and they are qualitative in nature. So we have come out with a solution to quantify the force and to give the doctors a way to log the data and measure the patient's recovery over time.
The main components that we'll be using in this project are the EZ430. The EZ430 is a development tool for the CC2500 and the MSP430F2274 combination. Now the MSP430F2274 is a low power microcontroller with appropriate peripheral and RAM availability as per our requirement. And we are using another EZ430 on the computer side, which will provide a link between the computer to use to log the data and the EZ430 in our application. The CC2500 is a low power RF module which works at 2.4 GHz spectrum. Now this RF module is also supported by the simplicity protocol used here. The op-amp that we are using for our sensors is OPA 4344, which is a low voltage precision op-amp, and the LDO which is being used in this application is a TLE 70436, which is a low cost LDO.
The sensors that we are using are a flexible piezoresistive sensor that we have fabricated ourselves. These sensors have a resistance of around 200 ohms when fully pressed with maximum force and around 40 kilo ohms when completely unloaded. These sensors are further connected to the OPA op-amps and used in a gain modulation circuit. Now how these sensors are made is basically by using a fabric called Velostat that is manufactured by 3M. This is a piezoresistive fabric made by 3M, and sandwiching multiple layers of Velostat on a conductive fabric like this will basically give us a sensor that responds to force and changes its resistance according to it. And these sensors, being completely flexible, can actually be stitched on any kind of fabric and they don't suffer any damage with deformation.
This is a prototype of our module. The module consists of 5 sensors which are connected to gain modulator, which is connected to a gain modulator circuit using OPA 4344. The sensors are piezoresistive sensors, as we mentioned earlier, which can be stitched on the exercise ball that we plan to implement. The EZ430 is also located on the same module, which will be located inside the ball. The other part of the circuit, the other part of the system is connected to the computer, which logs the data and provides the doctor a user interface to check the data which is stored in the microcontroller according to the finger grip measurement. We also have another sensor card which can be used to measure the force between two fingers and also the force between any finger and the thumb. These forces are important parameters in the medical field.
This is the interface that we've made for logging the force. Initially the port opens up and the computer connects to the local EZ430 module. Then after that there's a simple menu application to select the different functions. The first thing we need to do is form a link with the other module that's on the measurement device. and the jumper is used to enable the radio on the EZ430 of the mobile device, because otherwise the battery operated device will drain way too much power from the battery. Now, making the link, it says connection successful. After this, all the different fingers and the forces can be measured, and the sixth one that says specific measurements is used for the other auxiliary sensor that we provided, which can be used to measure the force between two fingers, or between the fingers and the thumb. So initially we look at the first finger, say the thumb, and the initial value is all zeros. The immediate value is a short-term recording and shows the instantaneous values of the force. The short-term recording is time averaged over a short period of time, and the long-term value is averaged over a large period of time. The count shows the number of times the person has pressed the sensor. So now we focus on the thumb, and we press the thumb sensor 3 times, and we look at the thumb data log one more time. It says total number of counts 3, and following that 46, 71 and 80 respectively are is the force exerted by the thumb on the 3 counts. Similarly, all the other fingers can also be measured in the following way. Right now we are pressing each of the fingers around 2 times. So looking at the index finger, we can see that it has registered 1 count with relatively less force. The middle finger has also registered 1 count. This is the ring finger. This has registered 4 counts, and the little fingers registered about 2 counts. Now moving on to the auxiliary sensor. For auxiliary sensor, we use the special measurements section, and this basically just gives us the maximum force exerted on this. So after we exert as much force as we can with our fingers, we stop the measurement, and the maximum force exerted is around 175. To find the short-term average of the force exerted on one of the fingers, say the thumb, we exert a force on the thumb sensor around 16 times. And we check the log again, and we have one short-term average of around 54, which is the average of all the values on the row above it. Now, to break the link with the EZ module on the patient, we choose the unlink option and we break the link.